A billion years from now, Voyager 1 will still be moving through the universe. No engine, no pilot, no signal, just drifting through stellar neighborhoods, galactic collisions, and the slow death of our own sun. What does that journey actually look like? The answer will genuinely rearrange how you think about time, distance, and what it means to exist in this universe. If this is the kind of content that genuinely lights your brain up, please subscribe to the channel. Now let's get started. Right now, as you watch this video, Voyager 1 is racing away from the Sun at roughly 61,000 kilometers per hour. Every single second, it puts another 17 kilometers between itself and everything we have ever known. But here is what makes this even more surreal. We are still talking to it. The signals it sends back travel at the speed of light, the fastest anything in the universe can move. And as of 2025, they take over 23 hours just to reach us. By November of 2026, Voyager 1 will hit a milestone no spacecraft has ever reached before. It will be one full light day from Earth. That means if engineers send a command in the morning, they will not get a response until the following morning. A 2-day round trip at the speed of light. Think about what that means. We built something in the 1970s that is now so far away that light itself takes an entire day to reach it. Now, before we can talk about where Voyager 1 is going, we need to understand where it already is, because it has already crossed a boundary that most people do not even realize exists. Our sun does not just shine light. It constantly blasts out a stream of charged particles called the solar wind, and this wind pushes outward in every direction, creating a giant invisible bubble around our solar system called the heliosphere. Inside this bubble, the sun's influence dominates everything. The planets, the asteroids, the comets, all of it lives within this shell of solar energy. For decades, scientists debated exactly where this bubble ends. Where does our solar system stop, and where does true interstellar space begin? On August 25, 2012, Voyager 1 answered that question for us. It crossed the heliopause, the outer boundary of that bubble, and became the first human-made object in the history of our species to enter interstellar space, the space between the stars. Nothing we had ever built had done this before, and when it crossed that line, the data changed dramatically. The plasma environment shifted. Cosmic ray readings spiked. Scientists looking at their screens in real time knew something profound had happened. Voyager 1 was out there, truly out there, alone in the void between solar systems. But here is a twist that most people miss, and I love this because it completely reframes how enormous our solar system actually is. Even though Voyager 1 has entered interstellar space by the measure of the solar wind, it has not actually left the solar system. Not yet, not fully, not in the gravitational sense. Our sun's gravity reaches far beyond the heliopause, far beyond the planets, far beyond anything visible through any telescope on Earth. There is a vast, spherical shell of icy objects surrounding our sun at almost incomprehensible distances, anywhere from 2,000 to potentially 100,000 astronomical units away. One astronomical unit, for reference, is the distance from Earth to the Sun, about 150 million kilometers. This shell is called the Oort cloud. Scientists believe it is the birthplace of long-period comets, those spectacular visitors that swing through the inner solar system once every few thousand years, dragging bright glowing tails across our night skies. Voyager 1 has not even reached the Oort cloud yet. It will not begin passing through it for roughly 300 years, and once it enters that region, it will take another 30,000 years or so to come out the other side. Only after that, somewhere around 40,000 years from now, will Voyager 1 fully leave the gravitational embrace of our Sun. Only then will it be, in every sense of the word, free. So what happens after that? What is the first landmark Voyager 1 will encounter once it is truly on its own? This is where it gets genuinely exciting. Based on precise trajectory data, including information from the European Space Agency's Gaia mission, which mapped over 1 billion stars with extraordinary precision, scientists have calculated exactly which stellar system Voyager 1 is drifting toward. In approximately 40,000 years, Voyager 1 will pass within about 1.7 light-years of a faint obscure star in the constellation Ursa Minor, the Little Bear, called AC plus 793888. It is a quiet red dwarf, nothing dramatic, nothing spectacular, but it is the first alien star system anything we have ever built will ever visit. 1.7 light-years is still an enormous distance. Voyager 1 will not be captured by this star's gravity. It will not slow down. It will not orbit. It will not stop. It will simply drift past silently, like a ship passing in the dark with no lights on. And there will be nobody on board to witness it. Strapped to the side of Voyager 1 is something I find genuinely moving every time I think about it. A golden record, literally, a gold-plated copper disc, 12 inches across, roughly 30 centimeters, containing sounds, music, and images meant to represent our entire civilization. It was designed by a team led by astronomer Carl Sagan, and it holds greetings in 55 human languages, the sound of rain, wind, and surf, the songs of humpback whales, Chuck Berry's Johnny B. Good, Beethoven, brainwaves recorded from a young woman thinking about falling in love. It is a message in a bottle thrown into the cosmic ocean, and that bottle will keep sailing long after every single human being alive today is gone, long after our cities have crumbled, long after our languages have changed beyond recognition. The record was built to last. Its golden casing, its protective aluminum cover, designed to survive for potentially 1 billion years in deep space. And that timeline matters enormously, because 1 billion years is exactly where this story is going. Speaking of distances that make your brain short-circuit, if you find yourself wanting to go even deeper into this feeling of just how strange and vast and unsettling space gets the further from home you travel, I made a full video on exactly that. It is called Why Space Gets More Terrifying the Further You Travel, and it picks up right where your sense of comfort ends. Seriously, go watch it after this one. I will link it for you. It will change how you think about distance itself. But first, we have only just scratched the surface of Voyager 1's billion-year journey, and the real surprises are still ahead. So let us set the stage for the question at the heart of everything. In 1 billion years, where will Voyager 1 actually be? This is not just a thought experiment. It is a real scientific question that real researchers have worked on seriously. In 2024, Harvard astrophysicist Avi Loeb and his undergraduate student Shokruz Kakarov used a detailed model of the Milky Way's mass distribution to trace the long-term trajectory of all 5 interstellar spacecraft ever launched, including Voyager 1, over billions of years into the future. What they found is both beautiful and deeply humbling. In roughly 1 billion years, Voyager 1 will have traveled so far that it will be on the opposite side of the Milky Way's disk relative to where our Sun sits today, the opposite side of our galaxy. The Milky Way stretches about 100,000 light-years across, and Voyager 1, drifting at 17 kilometers per second, pulled and shaped by the galaxy's own gravity, will have crossed something in the range of 50 to 60,000 light-years of galactic space. Not in a straight line, but through the sweeping, curving, gravitational choreography of the Milky Way itself. By that point, Voyager 1 will no longer be our spacecraft in any meaningful human sense. It will be a galactic traveler. And the Earth? By the time Voyager 1 reaches the far side of the galaxy, our Sun will have grown so hot and so luminous that it will have boiled every single ocean on our planet, every sea, every river, every drop of surface water, gone. The blue marble we call home will be a dry, scorched, airless rock. Whatever humanity has become by then, If we still exist anywhere, we'll not be here to mark the occasion. But that golden record will still be out there, still moving, still carrying the sound of whale song and Beethoven and a young woman's thoughts about love into the dark between the stars. Let us zoom out, way out. To understand what happens to Voyager 1 over 1 billion years, you cannot just think about the spacecraft. You have to think about the galaxy itself, the enormous, spinning, living structure that Voyager 1 is now a tiny passenger inside. The Milky Way is not static. It is not just a flat disk of stars sitting still in space. It is a rotating spiral galaxy, roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, swirling around a central core like water going down a cosmic drain. At the center of all that's spinning lies a supermassive black hole called Sagittarius A star, about 4 million times the mass of our Sun, anchoring the entire structure with its gravity. Our Sun, and by extension, the Earth, and by extension every human being who has ever lived, orbits this center at a distance of roughly 26,000 light-years. We are not at the heart of the galaxy. We are not at the edge. We live in one of the quieter suburban arms of a mid-sized spiral galaxy, and we complete one full orbit around the galactic center roughly every 225 million years. That trip around the galaxy is called a cosmic year, or a galactic year. And in the lifetime of Earth, 4.5 billion years, our planet has completed about 20 of them, 20 full laps around the Milky Way. Now imagine doing that in a spacecraft, without an engine, without anyone steering, just the raw pull of gravity from hundreds of billions of stars, slowly bending and shaping your path across the cosmos. That is exactly what is happening to Voyager 1 right now, and will continue happening for the rest of time. Here is something that might genuinely surprise you. When most people imagine Voyager 1's journey through space, they picture it traveling in a straight line, just shooting off endlessly in one direction forever, like a bullet fired into darkness. But that is not what is actually happening. Gravity does not care that Voyager 1 has left the solar system. The entire Milky Way has gravity. The dark matter halo surrounding our galaxy has gravity. Every dense region of stars, every spiral arm, every massive molecular cloud floating in the interstellar medium, all of it is pulling at Voyager 1 from every direction simultaneously, just in different amounts. According to the research done by Loeb and Kakarov at Harvard, the trajectory of Voyager 1 is not a straight line through the galaxy. It is a complex, curving, oscillating path that dips above and below the galactic plane as it moves. Think of it like a dolphin moving through water, not swimming flat along the surface, but arcing up and down through the medium as it goes. This vertical oscillation, moving above and below the flat disk of the Milky Way, is a critical detail, because it determines what environments Voyager 1 will pass through over billions of years. The galactic plane, the dense flat region where most of the galaxy's stars and gas clouds are concentrated, is a more chaotic, crowded, dangerous environment. The regions above and below that plane are quieter, emptier, more exposed to the open void between galaxies. Voyager 1, based on current calculations, will spend significant time oscillating through both. And each environment has very different consequences for the spacecraft's long-term survival. Let us talk about what Voyager 1 will actually encounter out there, because the interstellar medium is not empty. Not truly between the stars. Space is filled with a thin, almost impossibly diffuse mix of gas, dust, and high-energy particles. In most of the galaxy, this stuff is so spread out that you could pass through a cloud of it in a spacecraft and never notice. But over billions of years of constant exposure, even the gentlest rain of interstellar dust becomes significant. Researchers Nick Oberg and a colleague, using precise trajectory modeling informed by Gaia data, investigated exactly this question for the Voyager spacecraft. What happens to them over cosmic timescales? Their work, presented at a meeting of the American Astronomical Society, paints a fascinating and slightly sobering picture. As Voyager 1 moves through the galaxy, it will periodically pass through dense molecular clouds. These clouds are not gentle, tiny dust grains, some as small as 1/1000th of a millimeter, will slam into the spacecraft at speeds of a few kilometers per second. Each individual impact is minuscule, but over hundreds of millions, then billions of years, those impacts add up. They slowly erode the outer surfaces of the spacecraft. They chip away at the Golden Record's protective casing. But here is the remarkable finding from that research. Despite billions of years of exposure to cosmic dust, the Golden Record is still highly likely to remain at least partially intact for over 5 billion years. The information engraved on its surface, the sounds of Earth, the music of our civilization, protected by its aluminum casing and nestled against the body of the spacecraft, has a genuinely strong probability of surviving longer than Earth itself will remain habitable. Our planet will be cooked by the expanding sun in roughly 1 billion years. The message we sent into space could outlast us by 4 billion more. Now, back to that galactic journey. Recall that one galactic year, one full orbit around the Milky Way, takes roughly 225 million years for an object near our sun's position. But Voyager 1 is not near our sun's position anymore. It is moving away from the sun. It is following its own path through the galaxy, shaped by slightly different gravitational forces. According to the Harvard study, within 1 billion years, which is less than 5 galactic years, Voyager 1 will not complete a single clean orbit around the galactic center. Instead, it will trace a complex, looping path through the Milky Way that carries it to the opposite side of the galactic disk, relative to where the sun is, 50,000 light-years. Give or take, let that distance breathe for a moment. 50,000 light-years is so vast that even light, moving at just under 300,000 kilometers per second, takes 50,000 years to cross it. And a spacecraft drifting at roughly 17 kilometers per second will cover that distance in 1 billion years through the slow, patient pull of galactic gravity. It is not going in a straight line. It is being carried like a leaf on a river, swept through eddies and currents it cannot see or resist. Now, there is something the researchers specifically noted about this galactic orbit that is worth pausing on. The Milky Way's spiral arms are not solid, fixed structures like the arms of a spinning toy. They are regions of higher density, like slow-moving traffic jams where stars and gas tend to pile up temporarily. As the galaxy rotates, these density waves move through the disk, and stars spend time inside them and outside them in cycles. Over 1 billion years, Voyager 1 and our Sun will pass through multiple spiral arm crossings. Each crossing means moving into a denser region of the galaxy, with more nearby stars, more interstellar gas, more molecular clouds, and importantly, a higher rate of supernova explosions from massive, short-lived stars that form preferentially in those dense regions. Supernovae are stellar explosions so powerful they briefly outshine entire galaxies. From close enough, the gamma radiation they release could strip away planetary atmospheres. They seed the interstellar medium with heavy elements, the iron in your blood, the calcium in your bones, all of it forged in the cores of dying stars and flung outward by these cataclysms. Voyager 1 will not be close enough to any supernova to be damaged meaningfully. The distances are simply too vast. But it will be bathed in the slowly shifting cosmic ray environment that supernova remnants produce. It will drift through regions that are slowly being reseeded with the raw material for new stars, new planets, new worlds that do not yet exist. It is moving through the galaxy's ongoing story, a story that was being written long before Earth formed and will continue long after it is gone. Let us take a step back from the scale for a moment. because it is easy to get lost in light years and billions of years and lose the thread of what is actually remarkable here. Think about what Voyager 1 is. It is a machine, a collection of metal and wires and circuit boards assembled by human hands in the 1970s, guided by calculations done on computers less powerful than what now sits in your pocket. It weighs about 721 kilograms, roughly the same as a grand piano, and yet this piano mass of metal, thrown into the darkness nearly 50 years ago, is about to become a permanent inhabitant of the Milky Way galaxy, long after its last signal fades, probably sometime in the mid-2030s, when its plutonium-238 power source finally decays below the threshold needed to run its remaining instruments. It will still be moving, silently, blindly, without any power, any signal, any contact with Earth. It will drift for thousands of years before anything interesting happens, millions of years, and still it will drift. Through the cold dark between the stars, past alien suns that have never been touched by human eyes, through clouds of gas that are slowly condensing into worlds that will not solidify for millions of years yet, and it will carry with it the golden record, a message from a species that was curious enough, ambitious enough, hopeful enough to encode the sounds of its own heartbeat and send them into the unknown. There is something that Avi Loeb wrote about this that I keep coming back to, because it reframes the entire question of what Voyager 1's journey means. He pointed out that most stars in the Milky Way are older than our Sun. Some of them are billions of years older. If there are, or were, other civilizations on other worlds orbiting those older stars, and if they developed rocket technology similar to what we used for Voyager 1, their equivalent probes could already have been traveling through the galaxy for 1 billion years or more. Think about that. An alien Voyager, launched 1 billion years ago from a world we have never seen by a civilization we know nothing about, could be passing through our solar neighborhood right now, or could have already passed through it, or could be heading toward us. This is why scientists are paying close attention to interstellar objects passing through our solar system. In 2017, an object called Oumuamua passed through our solar system at high speed on a trajectory that was not gravitationally bound to the Sun. It was the first confirmed interstellar visitor we had ever detected. Its shape, its motion, its lack of a visible coma, all of it was strange. Unusual enough that a small number of serious scientists, including Loeb himself, could not fully rule out an artificial origin. We still do not know exactly what Oumuamua was, and in 2019 a second interstellar object, a comet called Borisov, passed through. This one looked more natural, but the fact that we are now detecting these visitors at all suggests the galaxy may be full of things moving between the stars. Objects sent deliberately or drifting naturally, crossing the void just as Voyager 1 will cross it. We are not just launching Voyager into the cosmos. We are joining a conversation that may already be happening, and we do not yet know if anyone else is listening. If you are enjoying this journey, make sure to subscribe to this channel and give a like. Every video we drop is designed to make you see the universe differently. Now let us talk about stars. Because over the course of 1 billion years, Voyager 1 is not just drifting through empty space. It is moving through a galaxy that is alive with stellar activity. Stars being born, stars dying, stars moving through space in their own slow, majestic orbits. And every now and then, Voyager 1 will pass close enough to one of them that the encounter actually matters. We already mentioned the first one. In about 40,000 years, essentially the blink of an eye on a cosmic timescale, Voyager 1 will pass within about 1.7 light-years of AC, plus 793888, a faint red dwarf in the constellation Ursa Minor. Based on NASA's own trajectory data, this is the closest stellar encounter in Voyager 1's foreseeable future. but 1.7 light-years is still an almost incomprehensible distance. For context, the closest star system to our Sun, Alpha Centauri, is about 4.2 light-years away. 1.7 light-years is closer than that, yes, but it is still so far that if you could somehow watch the flyby from the spacecraft, the red dwarf would appear as little more than a very bright star in the sky. There would be no dramatic close-up, no visible disk, just a point of light, slightly brighter than anything else around it, slowly shifting position over thousands of years as Voyager 1 drifts past. No dramatic greeting, no alien welcome party, just the quiet acknowledgement of proximity across the void. Now, something crucial happens once Voyager 1 clears the Oort cloud and enters true interstellar space, fully free of the Sun's gravitational grip. The rules of its journey change fundamentally. Inside the solar system, Voyager 1's path was dominated almost entirely by the Sun. Every planet it passed, Jupiter, Saturn, pulled at it slightly, but the Sun was always the dominant force. The trajectory could be calculated with extraordinary precision because there was essentially one massive gravitational anchor calling the shots. Out in the open galaxy, that changes completely. Now the gravitational landscape is a patchwork of thousands of competing influences, nearby stars, dense molecular clouds, the collective gravitational field of an entire spiral arm, the dark matter halo surrounding the galaxy. All of it contributes to Voyager 1's motion in ways that become increasingly impossible to predict with precision over millions and billions of years. This is why the Harvard calculations by Loeb and Kakarov are remarkable, and also why they come with honest uncertainty built in. They can model the broad shape of Voyager 1's galactic journey with reasonable confidence. They can tell us it will end up on the opposite side of the Milky Way disk in about 1 billion years. But the precise path it takes to get there, the exact stars it passes closest to, whether a particularly dense molecular cloud tugs it into a slightly different arc at some point 800 million years from now, that level of detail is genuinely unknowable, and I think that is actually beautiful. Even with all our mathematics, all our telescopes, all our computing power, the universe still holds mystery. It still has secrets it will not give up just because we asked politely. Let us talk about those molecular clouds for a moment, because they are one of the most consequential and least discussed features of Voyager 1's long-term journey. Molecular clouds are enormous concentrations of gas and dust scattered throughout the Milky Way. Some of them are absolutely staggering in size. The largest, called giant molecular clouds, can span hundreds of light years and contain enough material to form millions of stars. These are the stellar nurseries of the galaxy, the places where new suns and new planetary systems are slowly assembling themselves from the raw ingredients of the cosmos. They are also among the densest environments in the interstellar medium, which means they are where the dust erosion on Voyager 1 will be most significant. When the trajectory models developed by Oberg and his colleague accounted for these clouds, they found something interesting. The molecular clouds are not just passive obstacles. Their gravity is strong enough in some cases to actually bend Voyager 1's trajectory, to tug it into a new direction, to, as Oberg described it, fling it into a new orbit, sometimes deeper toward the galactic core, sometimes much farther out. This means that even if we could track Voyager 1 perfectly for the next 100,000 years, a single unplanned encounter with a particularly massive cloud could redirect its entire subsequent journey in ways that could not have been predicted from here. The galaxy is not a highway, it is a river, and rivers have currents. Here is a thought that tends to stop people in their tracks. You are made of stardust. You have probably heard that phrase before, and it tends to get thrown around so casually that it has almost lost its punch. But let us actually sit with what it means for a moment, because it connects directly to what Voyager 1 is about to spend 1 billion years flying through. Every atom of calcium in your bones was forged in the core of a dying star. Every atom of iron in your blood was created in a stellar explosion, a supernova so powerful it briefly outshone a galaxy. The oxygen you are breathing right now, the carbon in every cell of your body, the nitrogen, the phosphorus, all of it was cooked in nuclear furnaces inside stars that lived and died long before our sun was born. You are not just connected to the stars in some poetic, metaphorical sense. You are literally assembled from them. The same interstellar medium that Voyager 1 is drifting through right now, those diffuse clouds of gas and dust, is the raw material from which stars form, planets condense, and eventually life assembles itself. When you look up at the night sky and feel small, you are looking at your own ancestors. The atoms in your eyes were made in those stars. You are the universe looking at itself. And now we have sent a piece of ourselves, a small, golden-bearing piece of our civilization, back into that interstellar medium, back into the same kind of environment from which we came. In a very real sense, Voyager 1 is going home. Let us shift our attention now to something that will define the backdrop of Voyager 1's billion-year journey in ways that are almost impossible to fully appreciate. The long-term evolution of the Milky Way itself, because the galaxy that Voyager 1 is flying through today will not look the same in 1 billion years. It will not look the same in 100 million years. Galaxies are not static. They evolve, they grow, they merge, they transform. And our galaxy has a date scheduled. Right now, hurtling toward the Milky Way at roughly 110 kilometers per second is another galaxy, a big one. The Andromeda Galaxy, also known as Messier 31, is our nearest large galactic neighbor, sitting about 2.5 million light-years away, and it is heading straight for us. In about 4.5 billion years, the Milky Way and Andromeda will begin their collision. Now, here is an important clarification, because whenever people hear the word collision in this context, they tend to imagine stars smashing into each other like billiard balls. That is not what happens. Galaxies are mostly empty space. The actual stars within each galaxy are so far apart that the probability of any two individual stars directly colliding during a galactic merger is extremely low. What actually happens is more like two swarms of fireflies passing through each other. The gravity of both galaxies pulls and distorts and reshapes everything. Tidal forces stretch the spiral arms into long streamers. Stars get flung into wild new orbits. Some are thrown out of the galaxy entirely. Some fall toward the central black holes. The entire shape of both galaxies is warped and eventually destroyed. And over hundreds of millions of years, the two merge into a single enormous elliptical galaxy. Some astronomers have already given this future galaxy a name, Milkomeda. But here is the thing that is directly relevant to Voyager 1's journey. In 1 billion years, the time frame we are focused on today, the collision with Andromeda has not yet happened. We are still a few billion years away from that event. But the gravitational influence of Andromeda is already detectable. Its pull is already a real factor in the long-term dynamics of our galaxy's outer regions, and there is more. Recent observations, particularly from the James Webb Space Telescope, which has transformed our understanding of the early universe since it began operations in 2022, have revealed that galaxies interact with each other constantly. The Milky Way is surrounded by dozens of smaller satellite galaxies, some of which are slowly being absorbed. The large and small Magellanic Clouds, those two smudges of light visible from the southern hemisphere, are themselves satellite galaxies gradually being pulled into our own. Their gravity tugs at the Milky Way's outer regions, creating distortions in the disk. Voyager 1, by the time it reaches the far side of the Milky Way in 1 billion years, will be moving through a galaxy that has already been subtly reshaped by all of these interactions. The spiral arms will have shifted. Star formation rates will have changed. The interstellar medium will be different. The galaxy Voyager 1 finishes its first billion years in will not be the same galaxy it entered when it crossed the heliopause in 2012. Now, there is one more thing about Voyager 1's journey through the next billion years that I think deserves special attention. Something that is both scientifically significant and genuinely moving to think about. Voyager 1 is heading toward the constellation Ophiuchus. That is the general direction of its travel as it leaves our solar system. Ophiuchus is a large constellation sitting along the celestial equator, and it straddles the plane of the Milky Way. In Greek mythology, it represents a figure holding a serpent, Asclepius, the god of medicine. There is no particular significance to that mythological detail, but the fact that we can look up at a specific patch of sky and say, that is where it went, is somehow deeply moving. There is a direction, there is a heading, something we made and named and sent outward with a message of hope and curiosity, is moving toward a specific piece of the sky. In ancient times, people looked at constellations and told stories, connected the dots of light into heroes and monsters and gods. Now we have a machine drifting toward one of those patterns, carrying the sounds of our civilization, becoming part of the story that the universe is telling about itself. We do not know what, if anything, exists in the direction Voyager 1 is heading. We do not know if there are habitable worlds in that part of the galaxy. We do not know if anything with eyes will ever encounter it. But we sent it anyway, because that is what we do, that is what makes us human. The question, where will Voyager 1 be in a billion years, is on the surface an astronomy question. It is about orbital mechanics and galactic dynamics and the physics of interstellar space. And we have been answering it on those terms, and we will continue to in the next section. But underneath all the numbers and the light years and the timescales, it is actually a question about us, about what we value, about what we believe, about whether we think our existence, our music, our languages, our whale songs is worth broadcasting into a cosmos that may be completely indifferent to our presence. The people who built Voyager 1 answered that question in the only way that mattered. They did not debate whether it was worth it. They built it, they launched it, they attached a golden record and aimed it at the stars, and in a billion years, whatever we have become, wherever humanity's story has taken us, that golden record will still be out there, drifting through the far side of the Milky Way, still carrying our message, still moving. Let us talk about time, not the kind of time we deal with in our daily lives, the kind measured in minutes and hours and years, not even the kind measured in centuries, which already feels abstract enough. We are talking about deep time, geological time, cosmic time, the kind of time that makes a million years feel like an afternoon. Because one of the hardest things about this entire conversation, about truly understanding where Voyager 1 will be in a billion years, is that our brains are simply not built for these timescales. We evolved to think about seasons, about lifetimes, about a few generations at most. The idea of 1,000 years already strains our intuition. A million years is almost meaningless to us emotionally, even if we can write the number down. And a billion years? A billion years ago, the most complex life on Earth was a collection of single-celled organisms drifting in ancient oceans. Multicellular life had not yet invented itself. There were no fish, no plants, no insects, no dinosaurs, no mammals, nothing that would have been recognizable to us as alive in any meaningful, visible sense. Just microscopic life, slowly evolving in a world that looked nothing like the one we know. That is how long a billion years is. That is how far into the future we are projecting Voyager 1's journey. And somehow, a small machine built in Southern California in the 1970s is going to survive it. Now, one of the things that makes Voyager 1's long-term survival so remarkable is just how hostile the environment it is moving through actually is, in ways that are not always obvious. We tend to think of deep space as peaceful, serene. The word void suggests emptiness and quiet, and in many ways that is true. Compared to the surface of a planet, interstellar space is extraordinarily empty. But it is not passive, it is not benign. It is filled with energy and radiation and particles that, over billions of years, do real damage to physical objects. Cosmic rays are one of the biggest factors. These are high-energy particles, mostly protons and atomic nuclei, that travel through the galaxy at nearly the speed of light. They originate from supernova remnants, from the jets of active galactic nuclei, from the shock waves of stellar explosions across the entire history of the Milky Way. And they are everywhere. They pass through everything. Inside our solar system, the heliosphere actually provides a degree of protection against cosmic rays. The solar wind pushes back against them, reducing the flux of the most energetic particles that reach the inner planets. Earth's magnetic field adds another layer of shielding, but Voyager 1 has now left all of that behind. Out in interstellar space, it is fully exposed to the galactic cosmic ray environment. Every circuit, every wire, every surface of that spacecraft is being bombarded by these particles continuously. Over billions of years, this radiation slowly degrades materials, breaks molecular bonds, damages crystal structures, alters the properties of metals and ceramics. By the time 1 billion years have passed, the internal circuitry of Voyager 1, the computers, the electronics, the instruments, will be thoroughly destroyed by radiation damage. The spacecraft will be electrically dead in ways that go far beyond simply running out of power, but the structure will remain. The metal hull, the dish antenna, the boom that holds its scientific instruments, the golden record in its aluminum casing. These physical structures are remarkably durable. Metal does not decay the way organic material does. It does not rot or rust, at least not without the oxygen and water that cause those processes on Earth. In the vacuum of interstellar space, Voyager 1's body will persist essentially intact for an almost incomprehensible span of time. Long after every human civilization that has ever existed is a memory, long after our sun has swelled into a red giant and swallowed the inner planets, the chassis of Voyager 1 will still be drifting through the galaxy, carrying that golden disk. Let us talk about the sun for a moment, because its future is inseparably linked to the story of Voyager 1's journey and to the story of everything we call home. Our sun is a middle-aged star. It formed about 4.5 billion years ago from a collapsing cloud of gas and dust, and it currently sits comfortably in what astronomers call the main sequence, the stable, hydrogen-fusing phase of a star's life that can last billions of years. It has roughly another 5 billion years of main sequence life remaining, but stars do not simply fade out when their hydrogen runs low. They go through a dramatic transformation. As the hydrogen in the sun's core is exhausted over the next few billion years, the core will contract under gravity while the outer layers expand enormously. The sun will swell into what is called a red giant, growing so large that it could potentially engulf Mercury, Venus, and possibly even Earth. Its luminosity will increase dramatically during this process, and long before the actual engulfment, the heat alone will have catastrophic consequences for our planet. Current models suggest that in somewhere between 1 and 2 billion years, long before the sun reaches its full red giant phase, its increasing brightness will push Earth's surface temperatures past the point where liquid water can remain stable. The oceans will begin to evaporate. The water vapor will rise into the upper atmosphere, where ultraviolet radiation will break it apart. The hydrogen will escape into space, and Earth, the blue marble, the only home our species has ever known, will become a dry, scorched, dead rock. This is not a distant, abstract possibility. It is physics. It is the predictable, inevitable consequence of how stars work. And it means that when Voyager 1 reaches the far side of the Milky Way in roughly 1 billion years, the milestone at the heart of this entire conversation, nobody on Earth will be watching, nobody here will know. The planet will already be uninhabitable. This is the moment in the story where the human question becomes impossible to avoid. Will we still exist? Somewhere? 1 billion years is such a vast span of time that making any confident prediction about humanity's future feels almost absurd. Consider, anatomically modern humans have only existed for about 300,000 years. Recorded human history spans roughly 5,000 years. The industrial era, the age of science, technology, electricity, space travel, is less than 300 years old. In 300 years, we went from horse-drawn carriages to launching spacecraft beyond the solar system. What might humanity become in 1,000 years? In 1,000,000? In 1 billion? Some scientists and philosophers argue that if we survive the next few centuries, navigating the genuine existential risks that come with our current level of technological power, the odds of our long-term survival across cosmic timescales actually improve dramatically. Once a species becomes multiplanetary, spreading to other worlds, other star systems, it becomes extraordinarily difficult to destroy entirely. Others are more cautious. They point to the silence of the cosmos, the fact that despite decades of searching, we have not yet detected any confirmed signals from other civilizations, as a sobering hint that the long-term survival of technologically advanced species may be far rarer than we hope. We do not know, and that uncertainty is not a weakness of the science. It is an honest acknowledgement of what we do not yet understand. What we do know is this: in 1 billion years, regardless of what has become of humanity, Voyager 1 will still be moving. It does not need us to survive. It does not need anyone to remember it. It simply continues, indifferent and magnificent, carrying its golden message into a future that belongs to time itself. Now let us get specific about the galactic geography, because where exactly on the far side of the Milky Way Voyager 1 ends up is actually a fascinating detail worth unpacking. The Milky Way is not a uniform disk. It has structure, enormous sweeping spiral arms reaching outward from a central bar-shaped bulge of older stars. Our solar system lives in a region between two of these major arms, a smaller spur called the Orion arm, or sometimes the local arm. We are not deep inside a major spiral arm. We are in a relatively quieter interarm region. In 1 billion years, based on the Harvard modeling, Voyager 1 will be on the opposite side of the galactic disk from where the Sun currently sits. Now, the Milky Way disk is not perfectly flat. It has a slight warp, like a vinyl record left in the Sun, and its thickness varies across different regions. The disk is thinner in some places, denser and thicker in others. Where Voyager 1 ends up on that far side depends heavily on the cumulative effect of every gravitational nudge it receives along the way, from stars, clouds, the spiral arms it passes through. The broad destination is calculable. The exact coordinates down to any meaningful precision are not. And honestly, that feels right. A journey of 1 billion years should have some mystery left in it. What we can say with confidence is that Voyager 1 will be in a part of the galaxy it has never been near. A region of space where the stars look entirely different in the sky, where the constellations, from any hypothetical viewpoint near the spacecraft, bear zero resemblance to the ones we know. The Big Dipper would be unrecognizable, Orion would be gone. Our own Sun would be an unremarkable faint star among hundreds of billions of others, indistinguishable to the naked eye. From that vantage point, the Milky Way would still be visible as a band of light across the sky. But the view of it would be from the other side of the disk. The density of stars around Voyager 1 would depend entirely on which arm or interarm region it had wandered into. It could be moving through a rich stellar neighborhood, surrounded by young hot stars blazing with ultraviolet light, Or it could be in a quieter interarm void, where the nearest star is still light years away and the galaxy stretches overhead like a river of frozen light. We simply cannot know which, and that is part of what makes the question so endlessly compelling. There is a concept in astronomy called the cosmic perspective. It is not just about looking at the universe and feeling small, though that is certainly part of it. It is about recognizing that the universe operates on timescales and spatial scales so vast that our ordinary frameworks for understanding the world simply break down. When you look at Voyager 1's story through the lens of the cosmic perspective, something interesting happens to your sense of what matters. We spend enormous amounts of energy worrying about things that will not matter in 100 years, let alone a billion. Political struggles, economic crises, social conflicts, all of these things are real, and they matter deeply in the context of human lives and human dignity. I am not dismissing them, but when you zoom out to the scale of Voyager 1's journey, when you sit with the reality that in a billion years our oceans will be gone and our spacecraft will be crossing the far side of the galaxy, something shifts. You realize that the most enduring things human beings have ever done are not the wars we have fought or the borders we have drawn. They are the questions we have asked, the art we have made, the curiosity we have chased into the darkness, the golden records we have attached to spacecraft and thrown into the void, not because we were sure anyone would find them, but because asking the question felt worth it. Carl Sagan understood this. He is the one who pushed for the golden record. He is the one who, in 1990, convinced NASA to turn Voyager 1's camera around one last time before switching it off to take a photograph of Earth from a distance of about 6 billion kilometers. In that photograph, one of the most famous images in human history, Earth appears as a tiny pale blue dot, less than a pixel across, suspended in a ray of scattered sunlight. Sagan wrote about it in a way that still, decades later, makes it difficult to breathe. Look again at that dot. That's here. That's home. That's us. In a billion years, that dot will be a dry, scorched rock. But the spacecraft that took the photograph will still be moving through the galaxy, still carrying Sagan's golden record, still carrying all of us in the only way anything of ours will survive into that unimaginably distant future. Let us talk about something that does not get nearly enough attention when people discuss Voyager 1's journey, the golden record itself. Not just as a symbol, not just as a romantic gesture thrown into the cosmos, but as a physical object with a real scientific story about its long-term survival. Because the golden record is not just gold, and the story of what it is made of, how it was designed, and what it is likely to look like in a billion years is genuinely fascinating. The record is a 12-inch, roughly 30-centimeter, copper disc, electroplated with gold. Gold was chosen very deliberately. It is one of the most chemically inert metals that exists. It does not oxidize, it does not corrode, it does not react with the trace gases in the interstellar medium the way iron or copper alone would. It was chosen because it is extraordinarily stable over long timescales. The gold plating is not just decorative, it is protective. It is a deliberate engineering choice made by people who were thinking about billion-year timescales when they designed it. The disc is encased in an aluminum cover, also gold-plated, which serves as an additional shield against the physical environment of space. On the outside of that cover, engraved in a form meant to be decipherable by any sufficiently advanced intelligence, without any shared language or cultural reference, are instructions for how to play the record. A diagram showing the correct rotation speed, a pulsar map showing the position of our Sun relative to 14 known pulsars that functions as a kind of cosmic address for Earth, a drawing of a hydrogen atom, the most common element in the universe, used as a universal unit of measurement. The people who designed this were not naive. They knew the chances of any intelligence ever finding Voyager 1 are astronomically small. The galaxy is enormous. Space is almost perfectly empty. The odds that any other civilization, if one even exists, would happen to intercept this particular spacecraft among the vast emptiness of an entire galaxy are staggeringly low. They sent it anyway, because the act of sending it said something true about us, because the attempt matters, even without a guaranteed result. Now, what does the research actually tell us about the Golden Record's physical survival over 1 billion years? The work by Nick Oberg and his colleague modeled the erosion of the Golden Record across multiple simulated trajectories, accounting for cosmic dust impacts, radiation exposure, and the gravitational effects of molecular clouds. The results were striking in their optimism. Both Golden Records, on Voyager 1 and on Voyager 2, have a very high probability of remaining at least partially intact for over 5 billion years. 5 billion years, that is longer than the Earth has existed. That is roughly the remaining lifespan of our Sun. But the details are interesting. The outer face of Voyager 1's record, the face exposed to the space environment, will experience gradual erosion from dust impacts over that timescale. The surface will be pitted and worn. Some of the outermost layer of information may eventually become unreadable. The inner face, however, the face pressed against the spacecraft body, is far better protected. Nestled against the aluminum housing, shielded from direct exposure, it has a much stronger probability of remaining legible, essentially indefinitely. So imagine this scenario, one that Loeb himself described in his writing on this subject. Imagine a civilization, billions of years from now, in a star system somewhere on the far side of the Milky Way. Their astronomers detect an anomalous object drifting through their neighborhood. Something small, artificial, moving on a trajectory that does not match any natural origin. They intercept it, they examine it, and they find, pressed against the body of a long-dead spacecraft, a golden disk. They decode the instructions on the cover. They build a device to play it, and they hear, across 5 billion years of silence, the sound of thunder, the sound of wind, the sound of ocean waves, the song of a humpback whale, a piece of music by Johann Sebastian Bach, a greeting spoken in a language no longer spoken by anyone anywhere. They would know from that moment that they were not alone in the history of the universe, that somewhere in some star system on the other side of the galaxy, there had once been creatures curious enough and hopeful enough to send a message. That is not science fiction. That is a physically plausible scenario based on what we actually know about the durability of the Golden Record and the timescales involved. I find it almost unbearable in the most wonderful way. Let us pull back to the question of Voyager 1's galactic journey and address something that might be nagging at the more scientifically minded among you. We keep saying Voyager 1 will reach the far side of the Milky Way in 1 billion years, but how does it actually get there? It is not moving in a straight line. It has no engine. Nothing is actively pushing it. So what is actually carrying it across 50-some thousand light-years of galactic space? The answer is gravity, but not the gravity of any single object, the collective gravitational field of the entire galaxy. Here is how to think about it. The Milky Way is not just a collection of individual stars, each pulling on things independently. The mass of the galaxy, all the stars, all the gas, all the dust, and crucially all the dark matter, creates a smooth, large-scale gravitational field that permeates the entire structure. Objects moving through the galaxy are embedded in this field the way fish are embedded in the ocean. The field exerts a continuous, gentle force on everything inside it. When Voyager 1 cleared the Oort cloud and entered truly free interstellar space, it began to feel the galaxy's gravitational field more directly than it ever had before. The Sun's gravity, which had previously dominated, weakened with distance to the point where galactic gravity became the dominant influence. From that point on, Voyager 1 is essentially in a galactic orbit. Just as the Earth orbits the Sun and the Sun orbits the galactic center, Voyager 1 is now on its own orbit, a long, complex, looping path through the Milky Way, shaped by the mass distribution of the entire galaxy. The difference between Voyager 1's orbit and the Sun's orbit is that Voyager 1 is moving much more slowly relative to the galactic structure. The Sun orbits at about 220 kilometers per second relative to the galactic center, fast enough to complete one loop in 225 million years. Voyager 1 is moving far more slowly in the galactic reference frame, which means its orbital path will be very different, more elongated, more elliptical, taking it on a journey that sweeps it across a much larger portion of the galaxy over 1 billion years. The Harvard calculations traced this orbit using a detailed model of the Milky Way's mass distribution, including not just the visible stars and gas, but the dark matter halo, which contains most of the galaxy's total mass and plays a dominant role in shaping the large-scale gravitational landscape dark matter. We have never directly detected it. We cannot see it, feel it, or interact with it in any way we currently understand. But we know it is there because of the way galaxies rotate, the way light bends around galaxy clusters, the way large-scale structure in the universe formed. And it is the invisible scaffolding that will guide Voyager 1's path across the Milky Way for the next billion years. Think about that. A spacecraft we built with our own hands, navigating through the gravitational field of matter we cannot even see. Guided by the ghost architecture of the universe, there is another aspect of this journey worth dwelling on, one that connects directly to some of the most exciting current research in astronomy. As Voyager 1 moves through the interstellar medium over the coming millennia, it will pass through regions that are being constantly refreshed and reshaped by stellar activity. Stars are dying all the time. When massive stars, those with 10 or more times the mass of our Sun, reach the end of their lives, they collapse and explode as supernovae. These explosions are not just spectacular light shows. They are engines of chemical evolution. Supernovae blast the interstellar medium with heavy elements, all the atoms heavier than iron, that cannot be made in ordinary stellar fusion, created instead in the extreme conditions of a stellar explosion and flung outward at a fraction of the speed of light. These elements seed the clouds of gas and dust that will eventually collapse to form new star systems. The iron in your body came from a supernova that exploded before our Sun was born. The gold in the Voyager record, the same gold chosen for its chemical inertness and longevity, was forged in a neutron star merger, an event so violent and so energetic that it produces gravitational waves detectable across the universe. We know this because in 2017, the LIGO and Virgo gravitational wave detectors, alongside traditional telescopes, observed exactly such a merger, called GW170 August 17, and confirmed that these collisions of ultra-dense stellar corpses are a primary factory for gold and other heavy elements in the universe. So the golden record is made of gold that was forged in a neutron star collision. It is carrying the sounds of Earth into a galaxy that made those sounds possible, in a universe that forged the very material of the record itself in one of the most violent events nature is capable of producing. Everything is connected. The more you pull on any thread of this story, the more the entire tapestry comes into view. Let us return for a moment to the question of star encounters, because while the first confirmed close pass will happen in about 40,000 years with AC plus 793888, the question of what comes after that over millions and billions of years is worth addressing honestly. The honest answer is, we do not know precisely. And here is why. Stars are not stationary. They are all moving through the galaxy on their own orbits, and those orbits are constantly being subtly perturbed by gravitational interactions with other stars and structures. Predicting exactly which stars will be near Voyager 1's path even 1,000,000 years from now requires knowing the exact current positions and velocities of every star in the relevant region. And while the Gaia mission has given us the most precise stellar catalogue ever assembled, it still covers only a fraction of the Milky Way's total stellar population with the accuracy needed for such long-term predictions. What we can say is this: over the course of 1,000,000,000 years, Voyager 1 will pass through regions of varying stellar density. Some of those regions will be rich with stars, particularly when the spacecraft crosses through a spiral arm. In those periods, the odds of a relatively close stellar encounter increase meaningfully, but even a close encounter within, say, 1 light-year of another star is not a collision. It is not even necessarily a dramatic event for the spacecraft. At interstellar distances, even a star passing within a light-year exerts only a tiny gravitational pull on Voyager 1. It would bend the trajectory slightly, nudge the path, but it would not stop the spacecraft, it would not destroy it, and it would not capture it into orbit around the star. Unless Voyager 1 happened to pass extraordinarily close, within a few astronomical units, which would require a coincidence of timing and position so improbable it is effectively impossible to plan for, the spacecraft will simply drift through stellar neighborhood after stellar neighborhood, a silent ghost, observed by no one. There is something quietly profound about that image. A ghost drifting through neighborhood after neighborhood, seen by no one. We pour so much energy into the idea of being seen, of being remembered. Our entire civilization is built, in many ways, around the desire to leave a mark, to matter, to be witnessed, to have our existence acknowledged by someone outside ourselves. Voyager 1 will drift through the galaxy for 1,000,000,000 years, and almost certainly nobody will ever see it. The odds that any technological civilization would happen to intercept this specific object among the vastness of the Milky Way are vanishingly small. It will most likely travel its entire billion-year journey unseen, undetected, unwitnessed, and yet it carries a message that was made with love and care and extraordinary scientific creativity by human beings who knew the odds were against it and sent it anyway. That tells you something important about our species, not just about our technology or our ambition, about our hope, about our willingness to do something meaningful even in the face of near-certain obscurity. We are the only species on this planet, as far as we know, the only species in the observable universe that has ever done something like this, that has ever looked at the cosmos and said, "We want to say hello," even if no one is listening, even if no one will ever find our message. We want to reach. That reaching is not irrational, it is not naive. It is, I would argue, one of the most deeply human things we have ever done. Let us talk about what we have learned about interstellar space since Voyager 1 crossed the heliopause, because the data it has sent back has genuinely surprised scientists in ways that are still being analyzed and debated today. When Voyager 1 crossed into interstellar space in August of 2012, it did not just become a philosophical milestone. It became the first direct measurement instrument humanity had ever placed in the interstellar medium. Everything we knew about that environment before that crossing was inferred, deduced from observations made at a distance, from models, from theory. Voyager 1 changed that. For the first time, we had a probe actually inside the interstellar medium, sending back real data from a place no human-made object had ever been. And what it found was not entirely what we expected. One of the most significant surprises was the nature of the boundary itself. Scientists had expected the heliopause, the boundary between the solar wind and the interstellar medium, to be a relatively smooth, well-defined transition zone. What Voyager 1 actually measured was a region of significant turbulence and complexity. The magnetic field direction shifted. The particle environment changed in ways that did not perfectly match the leading models. There were oscillations, waves in the plasma density that suggested the boundary was not static but dynamic, breathing in and out in response to changes in solar activity. This matters because the heliopause is not just a boundary for our solar system. It is a protective shell. The solar wind that creates it pushes back against the galactic cosmic ray environment, reducing the flux of the most energetic particles reaching the inner planets. The fact that this boundary is more complex and dynamic than we thought has implications for understanding how much protection our heliosphere actually provides, and by extension, how habitable our solar system is over long timescales. Voyager 1, by crossing that boundary and measuring it from the inside, gave us data we could not have obtained any other way, and it continues to challenge our models even years after the crossing. The plasma wave instrument on Voyager 1, one of the few instruments still operating as of the mid-2020s, has detected oscillations in the density of the interstellar plasma that reveal something extraordinary. The interstellar medium is not silent. It hums, not in any way you could hear with your ears. Sound requires a medium dense enough to transmit pressure waves, and the interstellar medium is far too thin for that. But in the electromagnetic sense, in the sense of waves propagating through the tenuous plasma of interstellar space, the medium has a voice, it has structure, it has a signature. In 2021, a team led by Stella Koch-Ocker at Cornell University published a paper in Nature Astronomy announcing that Voyager 1 had detected a persistent, low-level hum of plasma waves in the interstellar medium, a continuous signal that had been present throughout the spacecraft's journey through that region. It was faint, almost impossibly faint, but it was there, consistent, steady, like the background murmur of a city heard from very far away. This was not something anyone had specifically predicted. The prevailing assumption had been that the interstellar medium between clouds would be relatively quiet, that plasma oscillations would only be detectable near denser structures. The persistent hum suggested instead that the interstellar medium has a baseline level of activity even in its most diffuse regions. The galaxy is not silent between the stars. It is quietly, continuously vibrating. Voyager 1, drifting alone through the dark, is listening to the galaxy breathe now. Let us connect that finding to something much larger, because the interstellar medium that Voyager 1 is traveling through is not just a passive backdrop to the story. It is an active participant in one of the most fundamental processes in the universe, the birth of new stars and planetary systems. The gas and dust that fill the space between the stars are not randomly distributed. They are constantly being stirred and compressed by the shockwaves of supernova explosions, by the stellar winds of massive young stars, by the gravitational tides of the galaxy's spiral arms. When these forces compress a region of the interstellar medium enough, gravity takes over. The cloud begins to collapse under its own weight. As it collapses, it heats up. If the conditions are right, nuclear fusion ignites at the center, and a new star is born. Right now, somewhere in the Milky Way, this is happening. Stars are being born in clouds of gas and dust, similar to the ones Voyager 1 will drift through over the next billion years. Planetary systems are forming around those new stars. And some of those planets, statistically, based on what we have learned from the Kepler and TESS missions, will be rocky, Earth-sized worlds orbiting at the right distance from their stars to have liquid water on their surfaces. Life, or at least the conditions for life, is almost certainly being assembled somewhere in the galaxy right now, while you are watching this video. While Voyager 1 is drifting through the interstellar medium, while the golden record waits in its aluminum casing for a recipient who may never come, we are not alone in the sense that the processes that made us are universal. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, is the chemistry of the cosmos. These elements are everywhere. The molecular building blocks of life, amino acids, sugars, nucleobases, have been detected in interstellar clouds, in meteorites, in the atmosphere of Titan, in the tails of comets. Life, if it exists elsewhere, would not be alien in its chemistry, it would be family. This brings us to one of the deepest open questions in all of science, one that Voyager 1's journey touches on in an unexpectedly direct way. Are we alone? The search for extraterrestrial intelligence, SETI, has been ongoing in various forms since the 1960s. Frank Drake pointed a radio telescope at two nearby sun-like stars in 1960 and listened for signals. He heard nothing unusual. Decades of more sophisticated searches have followed, using increasingly powerful instruments and covering wider ranges of the electromagnetic spectrum, and still, no confirmed signal. This silence is known as the Fermi paradox. The physicist Enrico Fermi, during a lunch conversation in 1950, posed the question in its simplest form. If the universe is so vast and so old, and if the ingredients for life and intelligence are so common, where is everybody? There are many proposed solutions to the Fermi paradox. Some argue that intelligent life is genuinely extremely rare, that the sequence of events required to produce a technological civilization is so improbable that we may be the only one in the observable universe. This is sometimes called the rare Earth hypothesis. Others argue that civilizations inevitably destroy themselves before reaching the stage of interstellar communication, through war, through environmental collapse, through the development of technologies they cannot control. This sobering idea has a name: the Great Filter. The question of whether the Great Filter lies behind us, meaning we have already passed through the most dangerous bottleneck, or ahead of us, is one of the most consequential open questions in human history. Still others argue that advanced civilizations do exist, but they are simply not communicating in ways we know how to detect. Perhaps radio waves are not their medium. Perhaps they are communicating with technologies so far beyond our current understanding that we would not recognize the signal even if we received it. And there is a more optimistic possibility, one that connects directly to Voyager 1's mission. Perhaps civilizations are communicating not through electromagnetic signals, but through physical objects, through probes, through golden records. If that is true, if the galaxy is seeded with the physical artifacts of civilizations that rose and fell across billions of years, then Voyager 1 is not just our message to the cosmos. It is also our declaration of participation, our announcement that we have joined the community, however vast and silent it may be, of species that have chosen to reach outward rather than turn inward. Let us spend a moment with the people who made this possible, because behind every number we have discussed, every light year, every kilometer per second, every billion years, there are human beings. Mathematicians and engineers and physicists who worked extraordinary problems with the tools available to them in the 1960s and 70s, without the computing power we take for granted today, and produced something that is still performing beyond expectations half a century later. The trajectory calculations that sent Voyager 1 on its grand tour of the outer solar system, using the gravitational slingshot effect of Jupiter and Saturn to accelerate the spacecraft far beyond what its own rocket could have achieved, required solving complex multi-body gravitational problems with a precision that was remarkable for the era. The concept itself, called gravity assist, had been proposed by a young scientist named Gary Flandreau in 1965, who realized that a rare alignment of the outer planets occurring in the late 1970s would make it possible to visit all of them in a single mission. That alignment happens only once every 175 years. If NASA had not launched in 1977, the opportunity would not have come again until the 22nd century. They did not miss it. The Deep Space Network, the array of giant radio antennas spread across 3 continents in California, Spain, and Australia, was built and maintained specifically to maintain contact with distant spacecraft like Voyager 1. Today, the signals from Voyager 1 arrive at Earth after traveling for more than 22 hours, weakened to a power level of roughly 10 to the minus 17 watts. That is 20 billion times weaker than the power needed to run a digital watch. And yet the Deep Space Network can still receive it, still decode it, still extract meaningful scientific data from a signal that has been traveling through interstellar space for nearly half a century. That is an engineering achievement as remarkable as the spacecraft itself. There is one more aspect of Voyager 1's physical design that deserves attention, particularly in the context of its billion-year journey. The spacecraft is powered by radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electrical power. No solar panels, no batteries in the conventional sense, just the steady, predictable decay of a radioactive element producing heat that is converted to electricity through thermocouples. Plutonium-238 has a half-life of about 87.7 years. This means that every 87.7 years, the power output drops to half its previous level. Voyager 1 launched with enough plutonium to generate about 470 watts of electrical power. By the mid-2020s, that had dropped to somewhere around 70 watts, barely enough to run a few instruments. NASA engineers have been performing extraordinary triage for years, carefully switching off instruments and heaters to conserve what little power remains, prioritizing the most scientifically valuable systems, extending the mission month by month with careful management. But the physics is unforgiving. Sometime in the next several years, likely before 2030, the power output will drop below the threshold needed to run any scientific instrument at all. At that point, Voyager 1 will go silent. The signal we have been receiving for nearly 50 years will stop, not because the spacecraft has been destroyed, not because anything has gone wrong, simply because the clock of its radioactive power source has finally run down. After that, Voyager 1 will still be there, moving, drifting, silent, the golden record still attached, still waiting, still carrying its cargo of human sounds into the dark. It will cross the path of AC plus 793888 in 40,000 years without us knowing. It will drift through the Oort cloud region without us tracking it. It will enter the truly open galaxy without us watching. We will have let it go, and it will continue anyway. There is something deeply moving about that moment, a moment that has not yet happened, but that we can already see approaching, the last signal, the final transmission from a spacecraft that has been our most distant ambassador for nearly half a century. When that signal stops, it will not be an ending, it will be a beginning, the beginning of the phase of Voyager 1's journey that is truly beyond us, beyond our knowledge, beyond our instruments, beyond our reach. A phase that will last not decades but epochs, not centuries but geological ages, not millennia but the full, deep, incomprehensible span of cosmic time. The silence, when it comes, will not be empty. It will be full of everything Voyager 1 carries with it into that silence, full of Bach and Beethoven and Chuck Berry, full of the sound of rain and the laughter of children and the greeting hello, spoken in 55 languages, full of the pulsar map that points back to a small blue world orbiting an ordinary star on the edge of one of 100 billion galaxies, full of us. And it will keep moving for 1 billion years, for 10 billion years, for longer than we have words to describe, moving through the galaxy that made us, carrying a message from the species that looked up at the stars and refused to stay silent. Let us talk about something that almost never gets mentioned in conversations about Voyager 1, and yet it is one of the most scientifically rich aspects of its entire story, the heliosphere. We have mentioned it before, the enormous bubble of solar wind inflated by our sun, stretching outward in all directions and carving out a region of space that is distinctly ours. But we have not fully explored what it actually is, what it does, and why Voyager 1's journey through and beyond it has permanently changed how we understand the relationship between our solar system and the broader galaxy. The heliosphere is not a simple sphere. That is the first misconception to clear up. The solar wind, the continuous stream of charged particles flowing outward from the sun in all directions, does not push equally in all directions against the interstellar medium. Our solar system is moving through the galaxy at roughly 20 kilometers per second relative to the local interstellar medium. This motion creates an asymmetry. The side of the heliosphere facing the direction of travel, called the nose, is compressed and pushed inward. The trailing side, called the tail or heliotail, is stretched out behind us, like the wake behind a boat moving through water. The result is a heliosphere that looks less like a perfect bubble and more like a comet, rounded on one side, elongated on the other. Some models suggest the heliotail extends for hundreds of astronomical units behind the Sun, possibly even further. We have never directly measured it. Voyager 1 is heading away from the nose region. Its trajectory does not take it through the heliotail, so we still have enormous uncertainty about the full three-dimensional shape of the bubble our Sun creates. This is one of the reasons scientists are so eager to continue analyzing every scrap of data Voyager 1 and its sister spacecraft Voyager 2, which crossed the heliopause in December of 2018, sends back. Each transmission fills in a small piece of a picture we are still assembling. Now, here is something that fundamentally reframes how you should think about the heliosphere, because it is not just an interesting structure. It is, in a very real sense, what makes complex life on Earth possible. The galactic cosmic ray environment outside the heliosphere is significantly more intense than what we experience inside it. The solar wind that inflates the heliosphere acts as a continuous shield, pushing back against the most energetic particles streaming in from the galaxy. Inside the heliosphere, particularly in the inner solar system, the cosmic ray flux is substantially reduced compared to what Voyager 1 is now experiencing in interstellar space. This matters for life. High-energy cosmic rays can damage DNA. They can ionize the upper atmosphere, affecting the chemistry of the ozone layer. Over long timescales, the cosmic ray environment can influence mutation rates in living organisms, potentially driving evolutionary change. And here is the fascinating part. The strength of this shield is not constant. It varies with the Sun's activity, solar maximum versus solar minimum, on an 11-year cycle, but it also varies on much longer timescales. When the Sun passes through a denser region of the interstellar medium, a molecular cloud, for example, the pressure of the incoming material can compress the heliosphere dramatically, reducing its size and potentially allowing more cosmic rays to penetrate to Earth's surface. Some researchers have proposed that these episodes of heliosphere compression, occurring as our solar system drifts through the galaxy over hundreds of millions of years, may have contributed to mass extinction events on Earth. The correlation is not perfectly established. This is still an active area of research, but the idea that the large-scale structure of the Milky Way has influenced the history of life on our planet through the mechanism of cosmic ray flux is both plausible and genuinely remarkable. The galaxy has not been indifferent to life on Earth. It has been shaping it, subtly and continuously, through the invisible architecture of fields and particles and moving clouds of gas. This connects to a broader idea that has been gaining traction in astrobiology over the past 2 decades, the concept of the galactic habitable zone. Just as there is a circumstellar habitable zone around individual stars, the range of distances at which a planet can maintain liquid water on its surface, some researchers have proposed that there is a galactic habitable zone around the center of the Milky Way, a ring-shaped region of the galaxy where the conditions for complex life are most favorable. The argument goes roughly like this: too close to the galactic center, and the stellar density is so high that close encounters between star systems are frequent, disrupting planetary orbits, bombarding planets with comets and asteroids, and exposing them to intense radiation from the supermassive black hole at the center. The environment near Sagittarius A star is extraordinarily hostile by the standards of what complex life seems to need. Too far from the galactic center, and the interstellar medium becomes metal poor, lacking the heavy elements needed to build rocky planets and potentially the biochemical machinery of life. The outer edges of the galaxy have lower concentrations of elements like carbon, oxygen, iron, and phosphorus, because those elements are produced in stars and recycled through stellar death events, processes that have been more active in the denser, more star-rich inner regions of the galaxy over its history. Our solar system sits in what many researchers consider the sweet spot, far enough from the dangerous galactic center, rich enough in heavy elements from billions of years of stellar recycling, in a relatively quiet interarm region that avoids the most intense episodes of nearby star formation and supernova activity. We may, in other words, live in one of the best possible neighborhoods in the Milky Way for complex life to emerge and survive. And when Voyager 1 crosses through the far side of the galaxy in 1 billion years, it will be moving through environments that are potentially quite different in terms of their habitability. Denser regions, harsher radiation environments, star formation zones buzzing with the ultraviolet output of young, massive stars. Voyager 1 will not care. It is a machine, immune to habitability concerns. But if there were eyes to look out from that spacecraft, the view of the galaxy from those regions would be spectacularly, overwhelmingly different from what we see here. Let us spend some time with a question that feels almost too big to ask directly, but that the entire story of Voyager 1 forces us to confront. What is the purpose of a message with no guaranteed recipient? The Golden Record was designed with extraordinary care. Carl Sagan and his collaborators, including Anne Druyan, who became his wife, and the musician and artist John Lomberg, spent months deciding what to include. They agonized over which music best represented humanity. They gathered greetings in dozens of languages. They recorded sounds: wind, rain, surf, crickets, frogs, the first cries of a newborn baby, the sound of a human kiss, chosen to represent the sensory experience of being alive on Earth. Anne Druyan, who served as the creative director of the Golden Record project, has spoken publicly about a remarkable moment during the recording process. While recording the electrical activity of her brain and nervous system, which was included on the record as a kind of biological signature, she was thinking about the history of ideas, about the experience of falling in love, about what it meant to be a human being alive in this moment in time. Those thoughts, encoded as electrical signals in her nervous system, were recorded and pressed into the grooves of the Golden Record. Her thoughts are on that record. Her experience of being human, whatever that experience was in those moments, is encoded in the grooves of a golden disk that is now beyond the solar system, drifting into interstellar space. It will outlast her body by billions of years. There is no word for what that is. It is not quite immortality. It is not quite communication. It is something new, something our species invented when we decided to throw a piece of ourselves into the cosmos and call it a greeting. Now, there is a scientific question lurking underneath all of this that we have been circling around, and it is time to address it directly. Is the golden record actually findable? The short answer is, in principle, yes. In practice, almost certainly not by natural chance, but possibly by deliberate search. Here is the physics. Voyager 1 is a small object, about 3.7 meters across at its widest point, including the dish antenna. In the vast emptiness of interstellar space, it is essentially invisible to any technology we currently possess beyond a few billion kilometers. We can only track it because we know exactly where it is, and we built a system, the Deep Space Network, specifically designed to receive its faint transmissions. Any civilization that did not know Voyager 1 existed and had not been tracking it from the beginning would have no way of detecting it passively. The spacecraft emits no significant heat compared to the background. It reflects no significant amount of light. It is, for all practical purposes, invisible. However, and this is where it gets interesting, a sufficiently advanced civilization with technology capable of systematic surveys of the interstellar medium might be able to detect it deliberately. Radar or LiDAR systems powerful enough to scan nearby interstellar space for anomalous objects, gravitational detectors sensitive enough to notice the tiny mass of a spacecraft drifting past, or, and this is the scenario that serious researchers have actually considered, a civilization that intercepted Voyager 1 while it happened to be passing through their solar neighborhood. The pulsar map on the Golden Record's cover is designed for exactly this scenario. If Voyager 1 is ever found, by chance, by deliberate search, by any means, the map provides the information needed to locate where it came from. 14 pulsars, each with their precise rotational frequency encoded, pointing back to a star we call the Sun. Pulsars are ideal cosmic landmarks precisely because their rotational frequencies change slowly and predictably over time. A civilization that found the record could use the encoded pulsar frequencies, accounting for the known rate of pulsar spin-down, to calculate not just where Earth is, but approximately when the record was launched. It is a timestamp as well as a map. We gave them the tools to find us. All they have to do is look. Let us return to the galactic journey one more time and add a detail that the Harvard study specifically highlighted, one that changes the picture in a subtle but significant way. The Milky Way is not moving through the universe in isolation. Our entire galaxy, along with Andromeda, the Triangulum galaxy, and dozens of smaller satellite galaxies, is part of a larger gravitational structure called the local group, and the local group itself is part of an even larger structure called the Virgo supercluster, a vast collection of galaxy groups and clusters spanning roughly 110 million light-years. On scales larger than the local group, the universe is expanding. Space itself is stretching, carrying galaxies away from each other at speeds proportional to the distance between them. This expansion, first discovered by Edwin Hubble in 1929 and found to be accelerating in 1998, a discovery that earned the Nobel Prize in Physics in 2011, means that on truly cosmic timescales, the universe becomes an increasingly lonely place. Within the local group, gravity is strong enough to overcome this expansion. The Milky Way and Andromeda, for example, are actually moving toward each other despite the universal expansion. But beyond the local group, every other galaxy cluster is receding from us, and over billions of years, the recession speeds of the most distant galaxies will approach and eventually exceed the speed of light, not because they are moving through space faster than light, but because space itself between us and them is expanding faster than light can traverse it. In the very long run, tens of billions of years from now, the observable universe will shrink. Galaxies outside the local group will disappear beyond our cosmic horizon, unreachable and eventually invisible. The universe will become darker, emptier, more isolated. Voyager 1's billion-year journey happens against this backdrop. The universe it is moving through right now, rich with galaxies visible in every direction, buzzing with the microwave background radiation left over from the Big Bang, is the universe at its most social in some sense. It will not always look this way, but in a billion years, the universe will still be recognizable, stars will still be forming, galaxies will still be visible, the Milky Way will still be a spiral galaxy, somewhat reshaped by interactions with satellite galaxies, but not yet merged with Andromeda, and Voyager 1 will be crossing through the far side of it, silent and golden, indifferent to all of it. There is one more thread I want to pull on before we move into the final stretch of this story, something that connects Voyager 1's journey directly to some of the most exciting science happening right now. The James Webb Space Telescope, which began full science operations in 2022, has been transforming our understanding of the early universe in ways that are still being absorbed by the scientific community. Its infrared vision has allowed it to peer back to the first few 100 million years after the Big Bang to see the very first galaxies that ever formed, smaller and more chaotic than anything in the modern universe, ablaze with the light of the first generation of stars. Those first stars, called Population 3 stars by astronomers, were made of almost pure hydrogen and helium, the only elements that existed immediately after the Big Bang. They had no heavy elements at all. No carbon, no oxygen, no iron, no gold. And because heavy elements are what allow planetary systems to form and life as we know it to emerge, those first stars almost certainly had no planets capable of supporting life. It took billions of years of stellar evolution, stars being born, living out their lives, dying in supernovae, seeding the interstellar medium with heavy elements, before the universe became chemically rich enough to support the kind of complex chemistry that life requires. We are, in a very real sense, a late universe phenomenon. Life like ours could not have existed in the early cosmos. The universe had to age first, had to process its raw materials through generations of stars before the right ingredients were available. We are the product of that long chemical preparation, and the golden record, made of copper and gold and aluminum, elements forged in generations of stellar death, is a physical embodiment of how far the universe has come from those first simple beginnings. Voyager 1 is not just traveling through space. It is a message from the late universe to whoever might be listening, a testament to what the cosmos is capable of producing given enough time and enough stars. Let us talk about what happens to Voyager 1 on timescales beyond 1 billion years, because while 1 billion years is the headline number, the milestone at the center of this entire conversation, the story does not end there. Not even close. The universe is 13.8 billion years old. 1 billion years from now, it will be nearly 15 billion years old, and Voyager 1, barring some extraordinarily improbable collision with a dense object, will still be moving. So what happens next? What does the 10 billion year version of this story look like? The 100 billion year version? These are not just thought experiments. They are legitimate scientific questions, and researchers have actually thought carefully about them. The answers are simultaneously sobering and magnificent. In roughly 4 to 5 billion years, the Sun will have exhausted its hydrogen fuel and swelled into a red giant. The inner planets, Mercury, Venus, and possibly Earth, will be engulfed or scorched beyond recognition. The outer solar system will be dramatically restructured. The Sun's mass loss during this phase will cause the orbits of the surviving outer planets to expand. The entire architecture of our solar system will be transformed. Around the same time, the Milky Way and Andromeda will be in the early stages of their collision and merger. The two galaxies will pass through each other, their stars mostly missing each other, but the gravitational distortion reshaping both into long, tidal streamers of stars, gas and dust. The night sky from any surviving world in either galaxy during this period would be breathtaking, filled with the sweeping, glowing structure of two spiral galaxies in the process of becoming one. Voyager 1, somewhere on the far side of the galaxy and beyond by this point, will drift through whatever environment the merger creates. Its trajectory will be affected by the reshaping of the galactic gravitational field. The smooth potential well it has been navigating for billions of years will become turbulent, complex, distorted by the gravitational waves of two merging galactic mass distributions, and yet it will keep moving. There is nothing in the merger of two galaxies that would stop a small, dense piece of metal drifting through the interstellar medium. It will simply be redirected, nudged into a new path through the chaos of the collision, emerging on the other side, still drifting, still carrying its golden cargo. In about 5 to 6 billion years, after the Sun has shed its outer layers as a planetary nebula, leaving behind the dense, cooling remnant called a white dwarf. What was once our solar system will be a quiet, cold place. The white dwarf sun will be slowly cooling over billions of years, its light fading from white to yellow to orange to red to eventually, in the far future, something close to invisible. Voyager 1, by this point, will be so far from the white dwarf formerly known as our Sun that its gravitational influence will be essentially negligible. The spacecraft will have fully decoupled from whatever remains of the solar system. It will be a pure creature of the galaxy, owned entirely by the Milky Way's gravitational field, or whatever the merged Milkomeda galaxy's gravitational field has become. The golden record's outer face by this point will be significantly eroded by billions of years of cosmic dust impacts. The surface will be pitted, worn, its finest details softened by the patient accumulation of tiny impacts over an almost incomprehensible span of time. But the inner face, sheltered against the spacecraft body, will remain largely intact. The information will still be there, the music will still be encoded in the grooves. The sounds of Earth, recorded in 1977, will survive the death of the Sun. Let that sink in for a moment. The Sun will die, and the music of Earth will still be drifting through the galaxy. Now let us think about something that requires a genuine shift in perspective, because most of this conversation has implicitly assumed that Voyager 1's journey is primarily about distance, about how far it travels, about where it ends up. But there is another way to think about it, a way that flips the entire frame. Instead of thinking about Voyager 1 moving through the galaxy, think about the galaxy moving around Voyager 1. Here is what I mean. From a certain perspective, the perspective of an observer sitting still relative to the cosmic microwave background, the deepest possible reference frame in the universe, neither Voyager 1 nor the Milky Way is sitting still. The entire galaxy is moving. The local group is moving. Everything is in motion relative to everything else in a cosmos with no fixed center and no absolute rest. Voyager 1 was launched by beings on a planet orbiting a star that is itself orbiting the center of a galaxy that is itself moving through the universe at roughly 600 kilometers per second relative to the cosmic microwave background. When we say Voyager 1 is moving at 61,000 kilometers per hour relative to the Sun, we are describing a tiny component of its total motion through the universe, its actual speed through the cosmos, accounting for the Sun's orbital speed around the galactic center, and the Milky Way's motion through the local group, and the local group's motion through the universe, is far, far greater. In a billion years, Voyager 1 will have moved through the universe on a trajectory that no coordinate system centered on Earth can fully capture. It will be embedded in a location in the cosmos that is genuinely new, Not just new relative to Earth, but new in the absolute sense of the word. A place in the universe that nothing from our solar system has ever been before. That is worth sitting with. We did not just launch a spacecraft into our galaxy, we launched it into the universe. And the universe is much larger than the galaxy. Let us talk about dark matter one more time, because the further we zoom out, the more central it becomes to understanding Voyager 1's long-term fate. We know that dark matter exists. We know this because the rotation curves of galaxies, the way stars orbit the galactic center at different distances, do not match what we would predict based on the visible mass alone. Stars in the outer regions of galaxies orbit far too fast. They should, by the logic of ordinary gravity applied to ordinary mass, fly off into space. The fact that they do not, the fact that galaxies hold together, implies the presence of a much larger invisible mass component whose gravity is doing the holding. This dark matter does not form stars. It does not emit light. It does not interact with ordinary matter through electromagnetism, which is why we cannot see it or touch it or detect it directly with any instrument we currently have. It interacts only through gravity, and perhaps through a force we have not yet discovered. The dark matter halo of the Milky Way extends far beyond the visible disk of the galaxy, perhaps 200 to 300 kiloparsecs in radius, which is roughly 600,000 to 1 million light-years. This invisible structure contains several times more mass than all the visible stars, gas and dust of the galaxy combined. It is the dominant gravitational structure of the Milky Way, and it is the dominant force shaping Voyager 1's billion-year journey. When the Harvard calculations modeled Voyager 1's galactic trajectory, they had to include a model of the dark matter halo in order to get physically meaningful results. The smooth, extended gravitational field of the dark matter halo, more important at large galactic radii than the contributions of individual stars, is the primary architect of Voyager 1's long-term orbit. We are navigating our spacecraft through a universe whose dominant component remains, after decades of intensive research, fundamentally mysterious. We know dark matter's effects, we know its distribution, we can map its presence through gravitational lensing and through the behavior of galaxies, but we do not know what it is. It could be a new type of particle, a weakly interacting massive particle, or WIMP, that fills the galaxy in an invisible cloud. It could be axions, extraordinarily light particles predicted by some extensions of the standard model of particle physics. It could be primordial black holes, formed in the first moments after the Big Bang, drifting unseen through the galaxy. It could be something entirely outside our current theoretical frameworks, something that requires new physics to understand. What we know is that whatever dark matter is, it is guiding Voyager 1 across the Milky Way, an invisible hand made of unknown stuff, steering a golden-bearing spacecraft through the galaxy. There is a moment that I keep returning to when I think about everything we have covered in this conversation. A moment that happened not in space, but in a conference room at the Jet Propulsion Laboratory in Pasadena, California. It was February 14th, 1990. Voyager 1 was approximately 6 billion kilometers from the Sun, far beyond Neptune's orbit, nearing the edge of the planetary solar system. The mission was effectively over. The cameras had been turned off to conserve power. There was no scientific justification in the strict sense for using the remaining power budget to turn the cameras back on. Carl Sagan pushed for it anyway. He lobbied NASA for months. He argued that the scientific value of photographing the planets from this extreme distance was secondary to the cultural and philosophical value, that seeing Earth from the outside, from deep space, would change how people understood our place in the universe. NASA agreed. The cameras were turned back on one last time. Voyager 1 was commanded to rotate, to point its camera back toward the inner solar system. It took 60 frames, a mosaic of the solar system from the outside, and in one of those frames, barely visible against a sunbeam scattered by the camera optics, was a pale blue dot, Earth. Seen from 6 billion kilometers, less than a pixel. Sagan wrote about that image in his 1994 book Pale Blue Dot, and the passage he wrote is, in my opinion, one of the most important things a human being has ever put into words. He wrote about how every king and peasant, every saint and sinner in the history of our species, lived out their lives on that mote of dust suspended in a sunbeam. He wrote about how our planet is a very small stage in a vast cosmic arena, and he concluded with words that feel, if anything, more urgent today than when he wrote them. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment the Earth is where we make our stand. Voyager 1 took that photograph. It showed us that image. It gave us that perspective. And then it kept going outward, beyond the planets, beyond the heliosphere, into the interstellar medium, carrying the golden record into a future that neither Sagan nor anyone who worked on the mission would live to see. Now, there is a question we have not yet addressed directly, one that feels almost too close to home to ask comfortably. Does any of this matter? Not in the abstract, philosophical sense, in the concrete, personal sense. Does Voyager 1's billion-year journey matter to you, to me, to anyone alive today or anyone who will be alive in the next few generations? We will not be here to see any of it. None of us will know what happens when Voyager 1 passes AC plus 793888 in 40,000 years. None of us will see the golden record recovered by some civilization on the far side of the galaxy in 5 billion years, if that ever happens at all. The journey we have been describing is so vast in time that it makes the entirety of human history look like a rounding error. And yet, I think it matters. I think it matters enormously, not because of what Voyager 1 will do in the future, but because of what it says about us now. It says that we are a species capable of thinking beyond ourselves, capable of caring about something that will not benefit us, will not be witnessed by us, will not be remembered by any living person we will ever know, capable of doing something beautiful and meaningful for its own sake, not for profit, not for power, not for immediate strategic advantage, but simply because it was worth doing. The golden record is not a message to aliens, not really. It is a message to ourselves, a statement about what we believe we are and what we hope we can become. It is humanity looking in the mirror and choosing to see something worth preserving in a world that often seems consumed by conflict and short-term thinking and the grinding weight of immediate problems. Voyager 1 is a reminder that we are also capable of this, of throwing a golden record into the stars, of asking the biggest questions, of reaching. If you are still watching, please subscribe to the channel. You will be part of a community that explores the cosmos together. Let us talk about what we do not know, because throughout this entire conversation, we have been speaking with a certain confidence, citing studies, referencing missions, describing trajectories and timescales with a precision that might give the impression that we have this all figured out, that the story of Voyager 1's billion-year journey is a solved problem, a closed book, a matter of simply reading off the numbers from a calculation that has already been done. It is not even close. The honest truth is that our understanding of Voyager 1's long-term fate is riddled with genuine, deep, scientifically important uncertainties. And I think it is worth spending some time with those uncertainties. Not because they undermine what we have discussed, but because they are actually some of the most interesting parts of the story. The edges of knowledge are where science lives. The places where we do not know are the places where the next generation of discoveries will happen. So let us be honest about what we do not know. First, the interstellar medium itself. Voyager 1 has been traveling through the interstellar medium for over a decade now, and in that time it has sent back data that has already surprised us multiple times. The density of the plasma varies in ways that were not fully anticipated. The magnetic field direction was different from what the leading models predicted. The boundary layer of the heliopause was more turbulent and dynamic than expected. What this tells us is that our models of the interstellar medium, the models used to calculate Voyager 1's long-term trajectory and survival, are good approximations but not perfect descriptions. The real interstellar medium is more complex, more variable, more structured than any model we currently have. This matters because the trajectory calculations for Voyager 1's billion-year journey depend on assumptions about the density and structure of the interstellar medium through which it will travel. If those assumptions are even slightly wrong in ways we cannot currently detect, and the evidence from Voyager 1's own measurements suggests they probably are, then the precise details of the trajectory will differ from what the models predict. The broad picture, Voyager 1 on the far side of the Milky Way in roughly a billion years, is likely robust. But the specifics, the exact path it takes, whether it passes closer to or farther from particular star-forming regions, whether a dense cloud encountered 300 million years from now nudges it significantly off course. All of that remains genuinely uncertain. Second, dark matter. We have discussed dark matter extensively, its role in shaping the gravitational landscape of the galaxy, its dominance as a mass component, its crucial contribution to the trajectory calculations in the Harvard study. But here is the uncomfortable truth that every researcher working on this topic would freely acknowledge. We do not know what dark matter is, and because we do not know what it is, we do not know with certainty how it is distributed on the small scales that matter for precise trajectory calculations. The models used in galactic dynamics, including the models used to calculate Voyager 1's long-term orbit, typically treat dark matter as a smooth, continuous fluid filling the galaxy's halo. This is a simplification. Dark matter is thought to form substructure, clumps, streams, filaments, on scales ranging from the size of entire dwarf galaxies down to potentially very small scales depending on the nature of the dark matter particle. If dark matter has significant small-scale structure, if there are dense clumps of dark matter scattered through the galactic halo that are not captured in the smooth models, then the gravitational landscape Voyager 1 will navigate over a billion years could be meaningfully different from what the calculations predict. A dark matter clump encountered 500 million years from now could nudge the spacecraft into a significantly different trajectory. We cannot account for what we cannot see, and we cannot yet see dark matter directly. Third, the long-term behavior of the Milky Way itself. The galaxy is not a static, predictable machine. It is a dynamic, evolving system subject to influences from outside as well as within. The Magellanic Clouds, the two satellite galaxies being slowly absorbed by the Milky Way, are already distorting the outer disk of our galaxy in ways that were only fully appreciated recently. Observations of the Milky Way's stellar halo have revealed streams of stars that are the remnants of smaller galaxies already absorbed in the distant past. The galaxy has a complicated history of mergers and interactions, and that history is still unfolding, predicting the exact state of the Milky Way, the position of its spiral arms, the distribution of its molecular clouds, the structure of its gravitational field. A billion years from now requires modeling a system that is inherently chaotic on long timescales. Small uncertainties in the current state of the galaxy amplify over time into large uncertainties in its future state. The Harvard study that gives us our best estimate of Voyager 1's billion-year trajectory was careful about this. The authors were explicit that they were providing a statistical picture rather than a precise prediction, a range of plausible outcomes rather than a single determined fate. This is good science. This is how honest uncertainty quantification works. But it means that the story of where Voyager 1 will actually be in a billion years has a wide range of possible chapters, not a single predetermined ending forth. What we have not discovered yet. This is perhaps the most important uncertainty of all, and the hardest to talk about, because by definition we cannot know what we do not yet know. But consider what we have learned just in the past few decades that we did not know before. We discovered that the expansion of the universe is accelerating, driven by a mysterious dark energy that makes up roughly 68% of the total energy content of the universe, and which we have no satisfying physical explanation for. We discovered thousands of exoplanets, reshaping our understanding of how common planetary systems are. We detected gravitational waves for the first time, opening an entirely new window onto the universe. We imaged a black hole directly. We began detecting fast radio bursts, millisecond flashes of radio energy from distant galaxies, whose origin is still not fully understood. Every one of these discoveries, dark energy, exoplanets, gravitational waves, fast radio bursts, was either completely unknown or poorly understood 25 years ago. Some of them require modifications to our theoretical frameworks. Some of them are still not fully explained. In another 25 years, in another 100 years, our understanding of the universe will be different again in ways we cannot predict. And some of those future discoveries will almost certainly affect how we understand Voyager 1's long-term journey. Perhaps we will discover new physics that reveals the nature of dark matter, allowing far more precise trajectory calculations. Perhaps we will understand the interstellar medium well enough to model it accurately over cosmic timescales. Perhaps we will discover something about the large-scale structure of the galaxy that changes the picture entirely. Science is not a completed edifice. It is a process, a continuous, self-correcting, endlessly surprising process of figuring out how things actually work. The story of Voyager 1's journey is not yet fully written. Some of its chapters will be filled in by discoveries that have not been made yet. There is something liberating about sitting with all of this uncertainty, about acknowledging honestly that we do not have all the answers, that the universe is more complicated than our current models, more surprising than our current theories, more vast and strange and wonderful than we fully understand. We live in a culture that is often uncomfortable with uncertainty. We want definitive answers. We want to know exactly what is going to happen and when and why. And science, good science, honest science, is sometimes frustrating in this regard, because it tells you what it knows and also tells you clearly what it does not know. And the second part of that conversation is just as important as the first. Voyager 1's story is full of things we know. It is also full of things we do not know, and it is the things we do not know, the open questions, the unresolved mysteries, the edges of the map where the known world fades into the unknown, that make the story worth continuing to tell. Let us bring it back to the present for a moment, because while we have been talking about billions of years, there are things happening with Voyager 1 right now, in 2026, as you are watching this, that are scientifically significant and worth paying attention to. Voyager 1 is currently experiencing one of the most remarkable episodes of its entire mission. In late 2023, the spacecraft developed a serious communications problem. One of its flight data system computers began sending back garbled data, unintelligible to engineers on Earth. For months, mission controllers at the Jet Propulsion Laboratory worked furiously to diagnose the problem across a communication delay of more than 22 hours each way. The fix they eventually developed was extraordinary. Engineers identified a corrupted memory chip in the flight data system, a chip that had likely been damaged by decades of cosmic ray bombardment, and devised a workaround that involved redistributing the affected code across other portions of the spacecraft's memory, with updates sent across 24 billion kilometers of space. The repair took months of careful, painstaking work, and it succeeded. Voyager 1 was restored to full communication capability in April of 2024, more than 46 years after launch. Think about what that means. A team of engineers repaired a memory fault in a computer system 46 years old, running on technology from the 1970s, located 24 billion kilometers away, using radio signals that took over 22 hours to travel one way. The software patch had to be written, tested, transmitted across interstellar space, received by a spacecraft whose computers have less processing power than a modern pocket calculator, and executed correctly, all with a 2-day round-trip communication delay, making any real-time interaction impossible. And it worked. This is not a minor footnote. This is one of the most remarkable feats of remote engineering in the history of technology, and it speaks to the extraordinary dedication of the people who have devoted their careers to keeping this spacecraft alive. Many of them young engineers who were not yet born when Voyager 1 launched in 1977, who have had to learn to work with systems so old that the original documentations sometimes has to be pieced together from physical archives. There is a poignancy to that image that I find deeply moving. Young engineers in the 21st century hunched over schematics of systems designed half a century ago, trying to keep alive the most distant human-made object in history. Not because it is commercially profitable, not because there is a clear return on investment, but because it is Voyager 1, because it matters, because the data it sends back from the interstellar medium is irreplaceable, data that no other spacecraft can provide, that no telescope can substitute for, that exists only because we kept this 50-year-old machine alive long enough to send it. There is a lesson in that, about what we choose to keep alive, about what we decide is worth the effort, about the things that matter not because of their practical utility, but because of what they represent. Voyager 1 represents our best self, our most curious, most ambitious, most hopeful self, the self that looks at the stars and feels not fear but wonder, the self that reaches not because it is easy, but because reaching is what we do. Now, as we approach the final chapter of this script, I want to address something that has been implicit throughout but deserves to be said clearly. The question, where will Voyager 1 be in a billion years, is ultimately a question about time, about our relationship to time, about what it means to do something, to create something, to send something into the world, whose consequences extend far beyond our own lifetimes and into timescales so vast they are essentially incomprehensible to the human mind. We plant trees whose shade we will never sit under. We build cathedrals that took generations to complete. We write books that we hope will outlive us. These are all expressions of the same impulse, the desire to participate in something larger than a single human life, to matter beyond the boundaries of our own existence. Voyager 1 is the most extreme expression of that impulse our species has ever produced. It will be moving through the galaxy long after every human being alive today is gone, long after every human civilization that has ever existed is forgotten, long after the Earth itself is unrecognizable. It will carry our message through timescales that make all of human history look instantaneous. And it was built by people who knew all of this, who understood that they would never see where it ended up, who understood that the message it carried might never be received, and built it anyway, designed it with care, with precision, with love, and sent it into the dark with a golden record full of everything they thought was worth remembering about being human. That is not a small thing. That is one of the largest things our species has ever done, not in terms of size or cost or technical complexity, though all of those are considerable, but in terms of what it says about what we are. We are the species that asks where Voyager 1 will be in 1 billion years. We are the species that sends golden records into interstellar space. We are the species that builds radio telescopes and points them at the sky and listens, really listens, for a voice that might be calling back to us across the darkness. We are the species that looks at a pale blue dot suspended in a ray of scattered sunlight and recognizes it as home. And we are the species that, in spite of all our conflicts and all our failures and all the very real ways in which we fall short of our own ideals, still manages to produce moments of such extraordinary beauty and vision and courage that they take your breath away. Voyager 1 is one of those moments, extended over nearly 50 years, and extending now into a future we cannot see but can imagine, a future in which a small golden-bearing machine drifts silently through the far side of a galaxy, carrying the sounds of a thunderstorm and a Bach prelude and a humpback whale's song into a silence that may last forever, or may not. Let us be clear about what we know one final time. We know that Voyager 1 is real, that it exists, that right now as you watch this it is out there, beyond the solar system, in the interstellar medium, moving at 61,000 kilometers per hour through a silence so vast that even our most powerful signals take over 22 hours to cross it. We know, based on the best available science, the Harvard study by Loeb and Kakarov, the trajectory modeling by Oberg and colleagues informed by Gaia data, decades of research into galactic dynamics and the interstellar medium, that in approximately 1 billion years, Voyager 1 will be on the opposite side of the Milky Way's disk from where our Sun currently sits, roughly 50,000 light-years away, drifting silently through a part of the galaxy it has taken 1 billion years to reach. We know that the golden record has a high probability of remaining at least partially intact for over 5 billion years, longer than the Earth will remain habitable, longer than the Sun will remain on the main sequence. We know that Voyager 1 will almost certainly never be found, that the galaxy is too vast, the odds too small, the silence too deep. But we also know that it is not impossible, that the pulsar map on the golden record's cover gives any finder the tools to trace their way back to where it came from, that the inner face of the record, sheltered against the spacecraft body, may remain legible essentially indefinitely, and we know that none of us will live to see any of what happens next, that the timescales involved are so vast that the entirety of recorded human history is a rounding error at the beginning of the journey, that Voyager 1's real adventure, the one that happens after the last signal fades, after the power runs out, after we have let it go, is a story that will unfold without us. There are things we do not know. We do not know whether there is anyone else out there, whether the Milky Way is full of civilizations that have been asking the same questions we are asking, building their own golden records, sending their own probes into the interstellar medium, or whether we are alone in a galaxy of 400 billion stars, the only voices in a vast and otherwise silent cosmos. We do not know which answer is more terrifying. We do not know what dark matter is, or why the expansion of the universe is accelerating, or whether the laws of physics we have discovered are the only laws that exist, or whether there are dimensions of reality we have not yet found the instruments to detect. We do not know what humanity will become in 1,000 years, or 1,000,000, or 1,000,000,000, whether we will still exist in any recognizable form, whether we will have spread to other worlds and other star systems. whether we will have found answers to questions that currently seem unanswerable, or whether we will have vanished from the universe without a trace, leaving only a golden record as evidence that we were ever here. These are not failures of science, they are invitations. They are the open doors that every generation of curious human beings is handed by the previous one, the unfinished business of a species that has been asking questions since before it had language to ask them in, and has not stopped yet. I want to end with something that I think captures the spirit of everything Voyager 1 represents. In 1977, the same year Voyager 1 launched, the astronomer and science communicator Carl Sagan wrote something that has stayed with me ever since I first encountered it. He was writing about the search for extraterrestrial intelligence, about the impulse to reach out into the cosmos and ask whether anyone is there. And he said something that I think applies not just to that search, but to the entire human enterprise of exploring the universe. And to Voyager 1 specifically, he said that somewhere, something incredible is waiting to be known. That is it. That is the whole thing, really. Somewhere, something incredible is waiting to be known, not guaranteed to be found, not promised to us, not available on demand, just waiting in the interstellar medium in the far side of the galaxy, in the nature of dark matter, in the question of whether life exists elsewhere, in the billion-year journey of a golden-bearing spacecraft that we launched into the dark half a century ago and have been tracking ever since with a mixture of scientific precision and barely concealed wonder. Somewhere something incredible is waiting to be known, and we are the species that goes looking, even when we are not sure what we are looking for, even when the distances are incomprehensible, even when the timescales dwarf everything we can hold in our minds at once. We go looking anyway. Voyager 1 is out there right now, moving, silent, patient, carrying Bach and Beethoven and Chuck Berry, carrying the sound of a mother's first words to her newborn child, recorded in 55 languages, carrying the electrical signature of Andromed's thoughts on a day she was thinking about what it means to be human, carrying a pulsar map that points back to a pale blue dot orbiting an ordinary star on the edge of one of 100 billion galaxies. In 40,000 years it will drift past a red dwarf star. In 1 billion years it will be on the far side of the Milky Way. In 5 billion years it will still be moving through whatever the galaxy has become by then, through the aftermath of the collision with Andromeda, through a universe that will be older and darker and emptier, but still enormous beyond comprehension, and the golden record will still be there, still carrying its message, still waiting. That is what we did. That is what we are capable of. That is what it looks like when a species that evolved on a small wet rock orbiting an ordinary star decides to reach into the cosmos and say hello. We do not know if anyone is listening. We said it anyway. And speaking of surviving the cosmos, if Voyager 1's journey made you wonder what it would actually take for us to make that trip, you need to watch the video on the screen. How long would we actually survive interstellar travel? Trust me, you are not ready for the answer.